All right, so in 5.1 we talked about how to find the area uh, under a curve. And we used rectangles to do that, and we set up a bunch of rectangles, and we said you can get an approximation um, to that area by using a number of rectangles. And then if you want a better approximation, you use more rectangles. And then you find the areas of those rectangles and add them all up, and that gives you a better approximation. If you want a better approximation, you do more rectangles. And we did that several times. In addition, we talked about ultimately you want to the more rectangles you cover your area with, the better approximation you get. Ultimately, you would like to cover it with an infinite number of rectangles. Um, and so we introduced that idea. We also introduced some idea of summation notations. So all of those things can be put together to actually start finding actual areas, not just approximations. So I just want to work through a problem here to show you how that is done. So here is the problem we want to work through. All right, so what we want to do is we want to look at this. The integral from 0 to 2 of x squared dx. Now, so that's our notation, but we know what that means. That means if we take the x squared graph, we're working with the x squared graph, and we want to find the area um, from 0 to 2. So there's 0, and there's 2. And so we are looking at finding this area right there. That's what we're after. We could cover it with rectangles, but we're going to go through the whole process of using Riemann sums and limits. All right, so we're finding the area between 0 and 2 under this curve. All right, so the first thing we're going to do is we're going to find delta x, and of course we know that is b minus a over n. So this will be the width of our rectangles. So in this case, 2 minus 0 over n. So 2 over n. If we cover that within rectangles, that will be our width. All right? Now we're going to use the right endpoint rule because that's the easiest notationally. And what that means is when we calculate the various values for the right endpoints, we're going to use this formula right here. So the x sub ith, so the right endpoint of the ith rectangle, is equal to x sub 0 plus I times delta x. So x sub 0 in our case is 0. We're starting at 0 plus I times delta x. So in other words, we just get 2I in. So those are the x's where we'll create the height of our rectangle. So right here, that's 2I over n. We go up that till we get to the top and then over. So that's our rectangle, all right? So what we know is that we're going to be plugging those values into our function, which is x squared, so 2I over n x squared, and so that's 4 over n squared, 4I squared over n squared, all right? And so those will be the heights of our rectangles. So the Riemann sum then is simply going to be the sum of I running from 1 to n of the height of each of the ith rectangle times the width of the ith rectangle. Okay? So if we work that a little bit, this will be the area of using n rectangles using the right-hand rule, 8I squared over n. Now notice we can do this. That summation only involves I, okay? So anything that's not an I can come out and be factored out. That's an important simplification step. Anything that is not involving I gets to come out. Oh, that's an n cubed. Let me lose that. So 8 over n cubed times the summation I equals 1 to n of I squared. All right? And that'll be the area of n rectangles. Now we can go even further than that because we know what this is. If I add up the first n I squareds, okay, we're going to get this. So we have the 8 over n cubed stays out in front. But if I add up the first n I squareds, it's going to be n times n plus 1 times 2n plus 1 over 6. Okay? I guess we don't need that. Again, so that's the actual sum. If we do a little algebra there, do some canceling, right? For instance, we can cancel a 2 out of there and there, leaving a 3 and a 4. I can cancel an n there with one of those n's. So we're left with just what? 4n plus 1, 2n plus 1 over 3n squared. Or if I just FOIL that out, it'll be 4 2n squared plus 3n plus 1 all over 3n squared. And this equals 8n squared plus 12n plus 4 all over 3n squared. And if I simplify that, it's going to be 8n squared over 3n squared plus 12n over 3n squared plus 4 over 3n squared. Or all told, it'll be 8 over 3 plus 4 over n plus 4 thirds, or 4 over 3n squared. Now the work is done for the most part. But again, that right there, that represents the sum of n rectangles, right? So if I did 8 rectangles, I could just actually plug 8 in there, and that would give me the volume, the area under those eight rectangles. It's really kind of neat that it simplifies down to this. If I want 16 rectangles, I would just plug 16 in for the ends, work out the math, and that would tell me the area of those 16 rectangles. I don't have to draw it. So it's nice that I get a full formula. But here's where the power really comes. Because we want the area, right? That's what this is saying. When I ask you for the integral, I don't want an approximation. I want the actual area. So what I need to do this is I need to find the limit as n goes to infinity of this sum. Right? I just want to imagine making more and more rectangles, and the way I do that is by taking the limit as n goes to infinity. And look what happens. This goes to 8/3 because it's constant, as in n has no effect. This goes to 0, and this goes to 0. So all told, that whole thing, that limit will be 8/3. The area under that curve, go back up here, the area under that curve, the exact area is 8/3. So if you take a look at this problem, that's how you do this if you want to find these areas. Okay, so we created our Riemann sum right here. Okay, and I guess it worked itself down to that right there. Then we used the little rule for adding up perfect squares to get rid of the summation. That was a key, is to be able to get rid of that summation symbol and change it with the formula. And then from there, it's algebra to get right here. And that is, again, that represents just the area under that we would have if we covered this with n rectangles. Then if we take the limit as n goes to infinity and are able to evaluate it, we can find the area.